Hello, everyone. In this section, we will introduce the characteristics of voltage buffer amplifier circuits in electronics. As mentioned in the previous video on the equivalent circuit of voltage amplifiers, if an amplifier has high open circuit voltage gain, but its input resistance Rin and output resistance Rout are not ideal, then its overall gain will also be unsatisfactory. In this situation, we need to use a voltage buffer amplifier. The characteristics of a voltage buffer amplifier are as follows. It has high input resistance, Rin, and low output resistance, Rout. However, circuits with this resistance characteristic usually have the following property. Their open circuit voltage gain is approximately 1. In other words, they do not provide voltage amplification. They are only used to adjust the input resistance, Rin, and the output resistance, Rout. A buffer amplifier is used in a cascaded connection. It improves the disadvantages of a high open circuit voltage gain amplifier, namely an input resistance that is too low and an output resistance that is too high. This connection of three amplifier circuits is called a three-stage cascaded amplifier. The signal Vs first passes through the first stage buffer amplifier, then goes to the second stage high open circuit voltage gain amplifier, then passes through the third stage buffer amplifier, and finally reaches the load terminal, RL. After replacing each of the three voltage amplifiers with its equivalent circuit, we can obtain the complete equivalent circuit diagram shown on the slide. From the equivalent circuit analysis of the three-stage amplifier, we can observe that the voltage signal source, Vs, is first delivered to the first stage buffer circuit. Therefore, the input signal of the first stage buffer circuit, Vi, equals Vs multiplied by R&B divided by the sum of Rs and R&B. This is because the voltage buffer amplifier has high input resistance. This can achieve Vi approximately equal to Vs. As a result, almost all of the signal source voltage, Vs, is delivered to the input terminal of the first stage amplifier without being lost across the signal resistance, Rs. In this way, we can solve the problem that occurs when using only a high open circuit voltage gain amplifier, whose input resistance is not high enough. However, the open circuit gain of a voltage buffer amplifier is close to 1. Therefore, when the signal is transferred from the output terminal of the first stage amplifier to the second stage amplifier, the output signal, which is also the input signal of the second stage amplifier, is first amplified by the open circuit voltage gain and then affected by the voltage divider effect between the output resistance of the first stage amplifier and the input resistance of the second stage amplifier. Therefore, Vi2 equals AVO times Vi multiplied by R and divided by the sum of Rout/B and Rin. At this point, we use the low output resistance characteristic of the voltage buffer amplifier. Therefore, Vi2 is approximately equal to AVOB times Vi and is approximately equal to Vs. This means that the signal transferred to the input terminal of the high open circuit voltage gain amplifier is equal to the signal source. This completely solves the problem that the input resistance Rin of the high open circuit voltage gain amplifier is not high enough. Next, let's look at the output side analysis. After the high open circuit voltage gain amplifier amplifies the input signal, the signal then passes through the voltage divider effect between its output resistance and the input resistance R/B of the next stage voltage buffer amplifier. We can obtain the signal value transferred to the input terminal of the third stage amplifier. Vi3 equals AVO times Vi2 multiplied by R/B divided by the sum of Rout and R/B. Because the output resistance of the high open circuit voltage gain amplifier is not low enough, when the signal is transferred to a load or to the next stage circuit, part of the voltage is lost across the output resistance, which reduces the output voltage. However, when a voltage buffer amplifier is connected at the output terminal, we can take advantage of its high input resistance characteristic. By taking advantage of its high input resistance characteristic, the signal amplified by the high voltage gain amplifier can be fully transferred to the input terminal of the voltage buffer amplifier. Therefore, Vi3 is approximately equal to AVO times Vi2. after obtaining VI3. After the signal is amplified by the third stage voltage buffer amplifier and then passes through the voltage divider effect between its output resistance and the load resistance, we can obtain the final output voltage signal delivered to the load. VO equals AVOB times VI3 multiplied by RL divided by the sum of R out B and RL. Then we use the low output resistance characteristic of the voltage buffer amplifier. Finally, we can obtain that the output voltage signal delivered to the load is approximately equal to VI3, and VI3 is approximately equal to AVO times VS. From this result, we can understand that a voltage buffer amplifier can effectively improve the poor input resistance and output resistance of the overall voltage amplifier. This is the purpose of the buffer circuit. Therefore, after voltage buffer amplifiers are used at both the input terminal and the output terminal, the overall gain of the entire circuit is approximately equal to the open circuit voltage gain of the high open circuit voltage gain amplifier. Almost perfect. Finally, let us compare this with using only a high open circuit voltage gain amplifier by itself, under the disadvantage that its input resistance is not high and its output resistance is not low. In that case, the overall gain will be much smaller than its open circuit voltage gain, depending on the resistor voltage divider effects at the input and output terminals. If voltage buffer amplifiers are used at both the input terminal and the output terminal of the high open circuit voltage gain amplifier, they can solve the input resistance and output resistance problems respectively. Finally, the overall gain can be approximately equal to the open circuit voltage gain. From the analysis of cascaded circuits, we can also understand another concept. As mentioned earlier, the complete circuit structure of a voltage amplifier can be divided into three parts: the signal source, the amplifier, and the load. However, in an actual circuit structure, the circuit you design may only be one part of many cascaded circuits. Therefore, it may not be directly connected to the actual signal source or to the final load. However, the concept remains the same. For the circuit you design, the signal source part is actually the output terminal of the previous stage circuit. In the equivalent circuit, it is still represented as a signal source and a signal resistance. The load terminal part is actually the input terminal of the next stage circuit. Therefore, the overall design structure and concept remain unchanged. The signal resistance of the signal source and the load resistance at the load terminal are determined by the previous stage circuit and the next stage circuit, respectively. Therefore, if the designers of the previous stage circuit and the next stage circuit are highly skilled, and their circuits have input resistance close to infinity and output resistance close to zero, then when you design your circuit, the signal source resistance you see, which is the output resistance of the previous stage circuit, will be zero. The load resistance you see, which is the input resistance of the next stage circuit, will be infinity. In that case, when designing your circuit, you do not need to worry too much if the input resistance and output resistance of your own circuit are not ideal, because they will not cause obvious signal loss. So, having strong teammates is a blessing because they can cover the weaknesses of your input and output resistance. That concludes the introduction to the characteristics of voltage buffer amplifiers. Please look forward to the content of our next class. See you next time. Bye-bye.